Hi everybody, RH here. I'm just looking for an opportunity to introduce myself. I have an extensive amount of experience teaching mathematics and working with a wide variety of students, all the way from algebra classes through high-end university level classes. What I want to do is just provide a little bit of a demonstration on how I work and what I can do to perhaps help you. So what we're going to look at first are a couple of items. Let me show you one of the most valuable tools we have today, which is Desmos, and talk about functions. So this is something that we use all the time in mathematics, but it isn't necessarily well explained. This is the type of thing that I can help with understanding. So ultimately, functions are just relationships between inputs and outputs. We think about x-axis and y-axis, but we really have a set of inputs, which I've represented with green dots, and outputs represented with red dots. And what I'm going to do is just modify the inputs here, and you can see the green dot moves, and as that green dot moves, the red dot moves as well. Those are the actual values of the function. You don't ever see it this way, but this is what we're talking about. So let me provide what you're more accustomed to seeing. Here is the mapping in that blue dot, which represents the input, in this case -4, and the output 5. And we write that down as an ordered pair. And then what you're really accustomed to seeing is the set of ordered pairs just represented as a line. So what you see most frequently is this shape here. In this case, we have a parabola. And what you'll notice is really what that parabola represents is the relationship between the inputs and the outputs, because a function is just that relationship between inputs and outputs. Let me give you another example. So in this example, we'll talk about singular value decomposition. If you're not familiar with that, that's fine. This is an animation I created which looks at the left singular vectors and the right singular vectors in SVD. The left singular vectors are the red vectors. They're always orthogonal. And what we're looking for is we're looking for the angle where the right singular vectors, the blue vectors, are orthogonal to one another. And so this graphic just demonstrates very easily for us to be able to see, hey, it's in this rotation, in this position, where we have the actual singular value decomposition. And there's a lot of explanation that goes behind that. But this is the type of thing that I like to do, is to help you understand what's happening. It's much easier to learn material if you understand what's happening. Let me just give you one more example. If what you're looking for instead of this is you're looking for computational help, no problem. Here's a common example. This is where we complete the square. Your teacher gives you a problem and says, hey, complete the square on this thing. We can talk about why we would want to complete the square, but we can also just work through the mechanics. We can take a look at the fact that, hey, the whole point of completing the square is replacing the terms that include some kind of an x with an actual squared value. In this case, and I'm not going to go through all the details, it's just a demonstration, we have something like x minus 3 squared. Well, where does that come from? Think about FOIL. We have x minus 3 times x minus 3, and you remember the FOIL, first, outside, inside, last. And when we do that, we would end up with x squared minus 3x minus 3x plus 9. And putting these together, this is going to be x squared minus 6x plus 9. And that's almost what we want. What we want is x squared minus 6x. So how would we modify this? We would just subtract 9. And now what we have is we have an actual exact representation for x squared minus 6x, which is what we were looking to replace initially. And then we just finish up from there. So we have our x minus 3 squared, remembering we have to subtract the 9. That gives us the direct replacement for x squared minus 6x. And now, of course, we have to add in the plus 10 is equal to 0. do that addition, and we have x minus 3 quantity squared plus 1 equals 0. And we've completed the square. We have a re-representation for the same equation that provides us with different information. This is the type of thing that we can talk about at length to help you not only with the conceptual understanding, but also with what are we doing, how are we doing it, why are we doing it, all the pieces. If I can help you, please just reach out and contact me. I'd love to have the opportunity to work with you. Thanks.